Hi gang, Dr. Stevens here with part 2 of the graphical solution of linear programs, finding the best solution. In our last video, we followed a 5-step procedure to go from a problem's formulation to a graph which showed the feasible region, the region of all possible points. In this lecture, we're going to find out how to find which one of those points is best. Here's a quick recap. Here was our formulation. We were talking about a company that makes and sells fireplaces. F is the number of fireplaces they make and sell, and S is the number of salespeople they have. The more salespeople, the higher the demand for the product. Their goal is to figure out how to maximize their profit in this operation. We formulated this program, and then we followed a 5-step procedure to find the feasible region that corresponded to it. This is a graph with axes for F, the number of fireplaces, and S, the number of salespeople, and a line that represents each possible constraint. An inequality constraint is satisfied by all the points on one side of its line, and the blue region that you see here, the feasible region, is on the good side of each one of the program's constraints. Any point inside that region will satisfy all of the constraints. Any point outside of that region will violate at least one constraint. That means as long as you stay inside the blue region, you're talking about a possible answer, and there's no point in looking outside the blue region because all the points out there are impossible. Some combination of F and S in this region is the best answer. For example, maybe it's here. That's a value of F equals 100 and S equals 10. Is that the best answer? Well, let's think about it a bit and see if we can figure out which of all those blue points might be the best. I want to make sure you see what's going on here, so let's stick with this particular solution for a moment. How good is it? Well, its quality is measured by how much profit it makes, and the top row shows the equation for profit. The red dot has F equals 100 and S equals 10, so I can stick those numbers into the profit formula and crank out the result. When the smoke clears, I've made $38,400 for that particular point. Not bad. Could I do better? Is there another point in the blue region where a similar calculation would give even more money? That's the question we want to explore, and I'm going to do it in a rather strange way. Right now you're looking at the feasible region standing upright on your screen. I'd like you to imagine laying it down on the tabletop, something like this. Now that red dot that we had a moment ago at F equals 100, S equals 10 is still there, and what I'm going to do is to pull out a big long piece of uncooked spaghetti and cut it to a length of 38.4 inches to represent the $38,400 of profit that we make at that point. Then I will glue it right on top of that red dot, standing straight up in the air. I'm going to do this, in principle at least, for every single point inside the feasible region. Take its coordinates, find the objective, cut a piece of spaghetti to represent that objective, and glue it on top of that point over the entire feasible region. Now, the question I want you to consider is, what's this field of spaghetti going to look like? If you look at the top of the spaghetti, what will the pattern be? It seems to me it would fall into one of 3 categories. First, maybe it's a chaotic mess, like a punk rocker's hair, just strands everywhere. The second possibility, gently rolling hills. The third possibility is more extreme. I'm talking about a surface which is flat, maybe tilted, but flat, like the facet of a diamond. Which do you think? Punk rocker hair, gently rolling hills, or that the top of the spaghetti will be flat but tilted like the facet of a diamond or a sheet of glass? I'll give you a hint. The objective is a linear function. And that makes all the difference. Because graphs that are linear will always graph as flat objects. If you only have one independent variable, it'll graph as a straight line. With 2 independent variables, it graphs as a plane. With more independent variables, it'll graph as a higher object called a hyperplane. But the point is, they don't kink, they don't bend, they don't jump, they don't dent. They are flat like a sheet of glass. So I'm saying that the top of the spaghetti is going to form a flat sheet like a pane of glass, maybe tilted at some angle. Maybe like this, maybe tilted like that, or it could be tilted some other way. But I want you to notice that no matter how it's tilted, you can always find a highest point or a lowest point on that pane of glass at a corner. In the first picture, it's the corner that's furthest away from us. In the second picture, it's the corner off to the left. It's the highest point that we want for a max solution. It's the lowest point that we want for a min solution. But now we're back to our original picture, And our original view of the feasible region is basically a top-down view, a helicopter view, looking straight down on this field of spaghetti. From this view, we can't tell where the highest point is or the lowest point is. Remember, the top of this picture is not high, it's north. The bottom is south, not low. We'd like to know where in this field is the tall spaghetti and where is the short spaghetti. All that we know right now is that the spaghetti tops are tilted like a pane of glass. How can we find that out? Interestingly enough, we can flood the field. Flood it a little bit. Here's a result. If you imagine that the field of spaghetti has a surface like a tilted pane of glass, it's easy to see what's going on. The water coming in from the northwest here has covered up the lowest part of the field, leaving the rest of the field out of the water. Notice that the line, the coastline between the water and the land is a straight line. Again, think of a pane of glass partially immersed into a pool of water, and you'll see why. Because the surface is flat, the coastline is straight. And as the water continues to get higher, you can figure out what's going to happen. Something like this. At this point, the water has continued to move parallel to itself until the last point is just sticking above the water on the right-hand side. We can see that that last point has to be the highest point in the field. Our last 5 steps are going to be doing exactly this same thing mathematically. First, we'll flood the field to some level and find out a straight line, which is a coastline. We'll be calling this an OFL. Then we'll see what happens as the field continues to flood. Notice that the tilt of the coastline has not changed. It stays the same as it moves across the field. That means the OFL will stay the same as well as we change the amount of water, as we change the value of the objective function. And what we're looking for is what's the last point which is left unhidden. Let's go and try. The OFL, the objective function line, is the flood line. And we're going to get it by setting the objective, which is the height of the spaghetti, which is the profit, to a specific number and seeing what the coastline graph is. What number? You pretty much can pick it. All the points on the same flood line will have the same profit. Pick a number and draw the line. Let's try it. I'm going to take my objective and set it equal to the number $13,400. If you like, that's the water level that I'm flooding over the field. That number is my choice. You can pick whatever you want. I picked that one because it happens to fit well on my graph. What I'm doing is taking my objective function and setting it equal to that number, and that will give me the equation of a straight line. All the points in my plane that have a profit of $13,400. You already know how to do this. We'll clean it up, and then we will find the f-intercept and the s-intercept, just like we did when we were doing straight lines. The f-intercept is 50, the s-intercept is -20, and so if we draw it, we get this, crossing the f-axis at 50, where the red dot is, crossing the s-axis at -20. Notice that I've drawn this as a dashed line rather than a solid line because OFLs are something different than borders. The constraints are the borders of the field. The OFL is the flood line, and as we flood more, that OFL will move. Every point on that line gives us a profit of $13,400. Every point on one side of the line gives us more. Every point on the other side of the line gives us less. Here it's not so obvious which way to go, is it? Let's play a little game. One side of the line has profits which are less than $13,400. One side of the line has profits which are greater than $13,400. That should sound familiar. Let's try a test point. I'm going to use 0, 0. If f is equal to 0 and s is equal to 0, plugging those numbers into my objective gives me a profit of negative $36,600, and that's certainly less than $13,400, which means that the side with the yellow cross is where the small profits are. The side on the other side is where the big profits are, and that's the direction that we're interested in moving. Please notice that the arrow does not necessarily point away from the origin, nor to the upper right. Because this is an aerial view, it could be pointing any direction at all. In this problem, it's a max problem. It is pointing toward the larger values, the parts of the field which are still out of water. If it were a min problem, I'd want the arrow pointing the opposite way, because I'd like small values, and $36,600 loss is indeed less than a profit of $13,400. But obviously we want to make some money here, so the arrow points the way we've shown it. Finding the optimal OFL is now going to be pretty easy. The coastline, as we steadily flood, will maintain a straight line shape, and it will maintain its same slope. You can imagine it gradually moving from the upper left to the lower right of the picture without changing its slope, and we keep on doing this until the very last point of the field goes underwater. You can see where it is, where the optimal OFL touches the feasible region. It's at the intersection of lines 1 and 2. We're going to say more about that optimal point in just a moment, but I do want to warn you about something that can at least apparently go wrong when you first start. Suppose that you drew your original OFL and it appeared like the one in this picture. As you can see, it doesn't cross across the feasible region. Many people will be tempted to figure that the arrow would have to point the opposite direction because the arrow, they think, is pointing to the optimal point. It doesn't. The arrow points to the direction where the high ground is for a max problem or the low ground is for a min problem. In our problem, the more water that comes in, the more our coastline would move in the direction shown. It would not move in the opposite direction. So whether your original OFL is to the left or the right or across your feasible region, it won't make any difference. Use the test point approach, or another approach that I'll teach you in a little bit, and draw the arrow in the appropriate direction. Once you get that arrow, even if your original OFL doesn't cross your feasible region, there's an easy way to make this process work. Take your original OFL, as you can see mine's off on the right-hand side of the graph, and imagine picking it up without changing its slope and dropping it over top of the feasible region. You see I've done that here marked with the Dragback OFL. The arrow on this one's going to be the same as the direction of the arrow on the first one. All OFLs in a single problem will have their arrows in the same direction. Then you can do your flood game again, sliding it across the feasible region until the last point goes under. That'll be the corner where at the intersection of lines 1 and line 2. So we found the optimal point. It has to be on the optimal OFL, and it has to be in the feasible region. Any point that meets those two conditions is an optimal point. In this problem, as you can see, there's only one. Most of the time there's only one, but sometimes there can be more, something called alternative optima that we'll talk about later. But for right now, we're almost done. All we need to do is to find the coordinates of that point with the star around it, the optimal point. And we can do that by realizing that it lies at the intersection of two constraint lines, line 1 and line 2. We'll use the equations of those lines to find the coordinates of that point. And this is the last step of the procedure. I've got my two constraints, the constraint line 1 and constraint line 2, written as equalities, and now I have to solve them simultaneously. Probably you learned to do this by taking one equation, solving it for one variable, and then plugging that expression for that variable into the other equation. Here, constraint 2 is already solved for one of the two variables. It's solved for f, which makes the substitution very easy. In the first equation, wherever I see an f, I'm going to replace it with the expression from constraint number 2, 120 plus 4s. Once I do, I have an equation that involves only s. And while it's not fun, a little bit of Algebra 1 will get you to the final answer, which is that s is equal to 13. That is, we should hire 13 salespeople. What's f? To find out, plug it back into the expression that we have in constraint 2. f is equal to 120 plus 4s, so that's 120 plus 4 times 13, or 172. Looking at the graph, those numbers appear to be about right. F looks like about 172, and F looks like about 13. This is the unique best answer to this problem, and we finish things off by figuring out how much profit it makes us. Take those values for F and S and plug them into the objective function, and we get a whopping $102,900. And that, ladies and gentlemen, is as good as it gets. The unique best answer to this problem.